Anyone who knows anything about fishing or shipping or boating or works in the maritime industry or sails knows about tides, the way the water level in a beach or bay rises and falls dramatically twice a day. Here in Scott's Bay, in the Bay of Fundy, New Brunswick, we can see some of the most dramatic tidal changes in the world. Every day has two low tides and two high tides, a morning tide and an evening tide. The ancient mariners believed that these tides were caused by the moon. And you know something interesting? They were right. The moon's gravitational pull attracts everything on the Earth, but it attracts the near side more than the far side because the near side is closer. That gives you a smaller denominator that gives you more force. See? Steve Sanders has done a great job of animating the force vectors for us, and you can see how much more force there is on the near side rather than the far side. Pull on one side of something stretchy, and I guarantee you it will stretch. As the moon pulls on the near side of the Earth, the water on the Earth's surface stretches and bulges one side towards the moon, one side away from the moon. Whichever the direction of the moon is, that's the direction of the two high tides. Now the Earth turns, so at any point during the day, you're going to be under first one and then the other of those high tides, passing through the low tides right in between.
For centuries, people have wondered about the role of the moon on ocean tides. Here's the moon in empty space. Not quite so empty, for in its vicinity, let's suppose there's a giant blob of water. For the moment, we'll assume both are at rest. If no external forces act on the giant blob, it's pulled inward by both surface tension and its own gravity to take the shape of a sphere, the shape having the least surface area. But there are external forces on the water. The moon exerts gravitational forces on the blob and forces that are not uniform. Since the force of gravity between two bodies varies as the inverse square of their separation distance, the moon pulls harder on the parts of water closer to the moon than in parts farther away. If the body of water is closer to the moon, the elongation is more pronounced. Not only are the forces greater, more importantly, the difference in forces between the closest and farthest parts is greater. Opposite sides of the blob seem to be stretched apart. Let's move the water back a bit and put planet Earth in the middle of it. And let the planet spin, say, one rotation each day. Looking down on the North Pole and watching Earth rotate, an observer at the seashore notices that the water is deep here, a high tide. Oh, notice the water is becoming less deep. And here we're at low tide, the best time to dig clams at the beach. Then the water begins deepening again. And before you know it, we have another high tide. The cycle continues. This computer animation makes this clearer. Nearer the moon, we see a greater stretch. Put a solid body inside the blob, move it out a bit, and here we see a North Pole view of Earth rotating daily beneath the ocean bulges. So with each rotation of Earth, we get two high tides and two low tides. So we see how Earth...
When it so happens that the sun and the moon are both in the same direction relative to the Earth, the sun adds its pull to the moon's, and we get what's called spring tides, higher high tides and lower low tides. When the sun is pulling one way and the moon is pulling another, we get neap tides, where the differences are less dramatic, lower high tides and higher low tides.